I have here a mixture of 3 different compounds: acetone, 2-butanone, and 2-pentanone. All 3 are examples of ketones, which are organic compounds that contain a carbon double bonded to an oxygen somewhere in the carbon chain, although not on the end because that would make it an aldehyde. As a chemist, I might need to analyze this mixture and find out how much of each is actually in there, and what is the total composition of this mixture. These ketones are volatile organic compounds, meaning they evaporate pretty easily and they have fairly low boiling points. This makes them ideal candidates for something called gas chromatography as a way to separate them and find out the total percent composition of the mixture. But what is gas chromatography and how does it work? Gas chromatography is a method by which we can separate volatile organic compounds by making use of their differences in polarities, intermolecular forces, and molar masses. These differences lead to different boiling points and a different ability for each compound to interact with the stationary phase and the mobile phase. There are many different types of chromatography, but they all share some basic characteristics. They all contain a stationary phase, some sort of surface over which the molecules need to travel, and a mobile phase which travels along the stationary phase and helps move the molecules along. Molecules that interact less with the stationary phase along the way will travel faster than those that interact with the stationary phase more. This leads to the separation of groups of molecules that have different properties. You can think of chromatography as a kind of molecular race. All the molecules are trying to make it to the finish line, but some get there a little faster than others. A typical gas chromatograph starts with the mobile phase, usually some sort of inert gas like nitrogen or argon, but sometimes room air can also be used. The flow of this gas is regulated by a regulator before it moves into the chromatography column. It enters the column, which is a long, coiled tube, sometimes containing inert porous material. Near the start of the column is an injection site, where a chemist can inject a small sample of the material to be studied. This material travels down the tube until it gets to the end where it's measured by a detector and then expelled as waste. This detector then allows a graph to be produced, which represents the number of molecules passing the detector at any given time. As a group of molecules reaches the finish line, a peak is formed on the graph. Each peak on the graph gives 2 very important pieces of information. First, it gives the retention time, which is the time that the material has been retained in the column before it had a chance to reach the finish line. Second, it gives a measure of the number of molecules making up a group. The larger the area under the peak, the larger the number of molecules of that component. To analyze the mixture using gas chromatography, you analyze the area under each peak, where each peak represents a different component of the mixture. Essentially, by calculating the area of each peak relative to the total area of all the peaks, you can analyze the percent composition of the mixture. The particular chromatograph that I'm using today contains an 11-meter stainless steel coil wrapped up inside this box. This coil is the stationary phase inside this instrument, and it uses room air as the mobile phase. The injection site is right here, and after the material goes through the column, it is ejected out the side as waste. It can be wired to this data collection device, or it can connect via Bluetooth. This data collection device produces the graph that we need and also helps with the analysis. Your gas chromatograph will likely need to be programmed for its test run. This includes choosing a starting temperature, a hold time if you want the temperature to remain constant for part of the run, a ramp rate if you want the temperature to slowly increase during the run, and a final temperature and a final total time. Once the program is set, it's time to draw up a small sample inside this special syringe, which is then placed inside the gas chromatograph. The plunger is then pressed the moment the data collection starts, releasing the molecules into the column. We first ran some trials using only one of the 3 ketones at a time to find out their retention times. We found the retention time of acetone to be about 2.2 minutes, the retention time of 2-butanone to be about 4.6 minutes, and the retention time of 2-pentanone to be about 6.6 minutes. This tells us that when the mixture is run, the acetone should show up as the first peak, while the 2-pentanone will show up as the last peak. We ran our mixture and we did find 3 peaks on our graph. Their retention times matched up nicely with those of the known samples, but the peaks were varying sizes. To analyze the mixture, we needed to find the area of each peak, a process called integration. and then compare it to the total area under all of the peaks. Thankfully, this device has an option that integrates any highlighted area, which made the process a lot simpler. We found our mixture to be about 16% acetone, 19% 2-butanone, and around 65% 2-pentanone. So, gas chromatography is a powerful tool for analyzing samples that contain volatile organic compounds. I hope you get a chance to do it in your chemistry travels, and if you do, I hope you found this video helpful. Thanks for watching, and have a great day.